Please silence your cell phones for the presentations. And Dave Eller will be introducing our first team for the afternoon.
Okay, I'd like to introduce Ryan Dallmier, Eli Ryder, and Zach Scheller.
Our project with printed circuit board, factory parts card, and JEDEC tray. Our scope. We had two tasks to our scope. We were to design and fabricate a feeder parts guard and design and fabricate a custom JEDEC tray. JEDEC is a Joint Electronic Device Engineering Council, and our liaisons were Dr. Cuban and Dr. Klobowski.
And the machine we had to work with was the Mancorp MC385B. It's a printed circuit board machine. It picks up circuits and then places them on the circuit board.
So the reasons for developing these parts for the PCB, mostly for the parts guard, was to protect the expensive feed reels. They add up really quick in cost. Also to keep people from bumping into the reels during operation and throwing the operation of the machine askew. For the JEDEC tray itself, this was designed to better organize the chip picking process during operation of the machine. And also, when you develop a custom JEDEC tray, it allows for more than one style of chip to be placed on a single tray in the PCB machine.
Here is the previous state of the PCB machine. As you can see, the feed reel protrudes out of the machine, and this is why we need the guard itself. It's easily bumped into by the operator with his knee, a cart wheeling around in the room, or even this air hose you can see in the picture here. It hangs from the ceiling. The reels are easily knocked off and damaged.
And our first proposed design would have just been a piece of steel bent into a U-shape with holes right here so it could mount in the machine. The pros for this it would be cheap to make, and it's a simple design. The cons are it's permanently mounted to the machine. It's not adjustable, and you'd have to drill and tap into the machine legs in order to mount it. And also there's wires running up and down the legs in that machine that you don't want to damage because it could void the warranty on it.
This is the second proposed design for the guard. The main advantage of this is that it's a removable design, and you can see that there's two cotter pins at each end of the guard, and that allows for it to be pulled straight out. The disadvantages of this design is that it's non-adjustable, meaning that it can't be adjusted from up to down positions. It's only straight out. And another disadvantage is that you'd have to drill and tap new holes in the legs of the machine, which, as Zach said earlier, would void the warranty, and there's a lot of wiring in those legs, and we didn't want to mess any wiring up.
This is our third and final chosen design. We like this design because, like the last one, it was removable, but this one is adjustable. It has two set points, two different heights you can set the guard to, and it can also be let all the way down, which would allow for the operator to work on the machine, replace any reels in the feed part. It won't void the machine, and we like this about the design because we use the existing bolt holes. In a future picture I'll show you what I'm talking about there. We won't have to tap into the machine or void any warranty with this design. And here's just 3 different views of our chosen design. Here in this picture you can see the 2 bolt holes on each side. Those come out, and that allows you to take out the guard itself if need be to work on the machine or get into the machine.
And you can see by the brackets right here, there's a lid on the PCB machine that allows you to access to put in circuit boards and chips. These cuts right here allow that lid to be open. And the materials we use for the brackets, we used A36 steel, 1/4 inch. That was for strength. And for the guard, we used 60-61 aluminum square tubing, 1.5 inches, and that was because it was lightweight and strong.
Here you see the existing bracketry that's already on the PCB machine. The one on the left is the keyboard bracket, and the other is a tray bracket. Those two bolt holes that are already existent there, those bolts were removed and the existing bracketry was taken off. Then the new bracketry was slid in behind it, sandwiched between the two, and longer bolts were used to hold the bracket in place. So there was absolutely no tapping or drilling required with this design. And also, the new bracketry didn't hurt the location of the USB ports.
Here is our final product and our finished design on the PCB machine. Here is the two different settings on the machine, two different heights you can set to. And as you can see, our bracket behind the already existing keyboard bracket, it does not, like Eli just said, it doesn't interfere with the USB ports. And it doesn't interfere with the reels while they're in production either. There's a good amount of room right there between the guard and the reels.
And for our economic analysis, we assumed that a heavy cart ran into the machine and it broke the parts feeder and the reels off of it. And to the replacement cost for the feeder would be $1,000. And then we assumed that it would take about 2 hours for a laborer to come out and put it on the machine, which would cost you about $102. And the total cost of that came out to $1,102. The cost to make the parts guard, we started with 40 hours of design labor. It took us 3 hours to weld it up, 2 hours to put it on the machine and paint it. And the student worker rate we assumed was $15 an hour. Our cost of materials came out to $410, with the total cost coming to $1,085. And this graph shows our break-even point. As you can see, $1,085 is here, so within the first incident, you've already got your money back. And this is just the total cost for 3 findings: $1,100, $2,200, and $3,300.
So there are two methods that the PCB picks and places chips. The first is the feed reels, which we described earlier, and we built the guard for. And the second is with the JEDEC tray. As stated earlier, JEDEC stands for Joint Electron Device Engineering Council. These trays are usually 1/4 inch thick, and a standard JEDEC tray has dimensions of 12.7 inches long by 5.3 inches wide. The main purpose of these trays is to allow for safe transport, ease of use in the machine, and safe handling.
Right here is the current state of the PCB machine. As you can see, the chips are just placed on a piece of particle board in the machine, and there's no organization at all whatsoever. There's no way for the machine to know where a certain chip is and where the next one is. There is a vision system on the machine, but it's not very effective the way the layout is currently on the machine. And if the machine were to be knocked around or hit at all, then the chips can be moved and knocked off.
So the objective in producing a JEDEC-style tray for the printed circuit board machine, we needed something that could be easily organized. It had to be capable of holding several chips, not just one single chip. It needed to be able to fit nicely in the existing aluminum plate that was already in the PCB machine without making any modifications at all. It needed to be durable, durable enough to withstand continuous use on a daily basis. And it had to fit the parameters of these 4 chips. Texas Instruments LB125, Freescale Semiconductors microprocessor, an Interseals SSOP, and Cardinal Components crystal oscillator.
Here, we're just going to go through and show you the different chips that we had to design the JEDEC tray for. This is a Texas Instrument LB125 in its dimensions, a Freescale Semiconductor, an Interseal, and a crystal oscillator.
So the way that the PCB machine knows where the chips are at and how it picks and places them is by way of an air nozzle. And here you can see the several different varieties of air nozzles that are used. The operator centers the nozzle with a vision camera on the center of the chip, and when that center is verified, the machine can then calibrate and determine the horizontal distance that it has to move to pick up the chip. Then it can pick and place those chips accordingly, and the size of the nozzle can vary. Obviously, a smaller nozzle for a smaller chip and a larger nozzle for a larger chip. And here we have a video of it determining the height of a chip placed in the JEDEC tray. You can see the JEDEC tray fits quite nicely in the tray that's already in the PCB. There's 2 clips on the left end that it fits snugly against. There's the spring-loaded probe moving down, detecting where the top of the chip is, and then it's going to back off. And the machine then has that data for future use.
Placement of the JEDEC tray, as you can see, indicated here on the right with the yellow arrow. It butts up in the right-hand corner and is snapped into place with some spring-loaded clamps on the left-hand side. This allows for organization of the chips. So when you calibrate the machine, like it was just shown before, it knows where those chips are, it knows where the next one is, and it's not all just, in chaos like you've seen before. This keeps them, if the machine is bumped in any way, the chips are not moving around. It just keeps the chips consistently in a place where the machine can pick them up and it can be more effective in production.
And this is a drawing of the design we came up with for the JEDEC tray. As you can see, there's 4 different slots for 4 of the each different kinds of chips we have. It's important to know that there's a 0.3 millimeter clearance on the X and the Y coordinates of those chip holders, and it will hold 40 of the Texas Instruments LV-125s, 28 of the Intercells, 28 of the Freescales, and 30 of the crystal oscillators in one tray.
So before we could print the entire JEDEC tray, we felt it was necessary to print a test tray, which is the same length as the entire JEDEC tray, but it's only a fraction of the width. This was done to make sure that the lengthwise dimension could fit into the tray on the PCB machine snugly. Another reason we printed a test piece was to make sure that not only were the clearances going to be accurate for the chips themselves, but also to make sure that our 3D printer was capable of printing down to clearances that small, which we found it was more than capable of.
Here's our finished JEDEC tray. On the left is a SolidWorks picture, and on the right is an actual finished product printed picture. We used the Fortis 400MC 3D printer here on campus to do this, and we chose the ABS M30i plastic. We found that to be the best choice because of its durability. This JEDEC tray is 12 3/8 inches long by 5 inches and 0.4 inches in thickness. Now in the design, we had to put 0.25 inch clearance between each chip, and that is between here, 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 and here, between your 4 different types of chips. And this is so that the machine knows where the other chips are at. So when you come in and you calibrate and you tell the machine, this is the chip, you have to tell the machine where the distance is between the next chip so that it knows where all these chips are. And then when you calibrate this one, it knows where all these are and so on.
And this is just a video of the pick and place machine actually picking parts up out of the JEDEC tray. As you can see right now, it's switching nozzles. And then it picks up a part from the JEDEC tray and places it on the circuit board.
So for the cost analysis, the cost of printing on USI's campus is approximately $15 per cubic inch. Our JEDEC tray uses 14.5 cubic inches of material, which equates to $218. I priced the volume of what our JEDEC tray has through a company called 3dprintingpricecheck.com. It's really an actual website. And with a similar ABS material that we have, they wanted $57 per cubic inch, and that's just for printing. That doesn't include the design. So that equates to $827. Also, the average price of a single chip standard JEDEC tray is $10. So if you had to buy one tray for each of the 4 chips that we have, that's $40. However, you have to take into account that if you have a set amount of chips that you need to purchase, you're going to have to buy the tray with each of those chips as well, because the tray is pre-formed to the chips themselves. And that can add up quickly.
Future improvements we would like to see to the PCB machine. Right now, we just have the guard painted. We would like to see a powder coat to the guard. And with the JEDEC tray, we'd like to see rubber placed underneath so that the components don't easily slide on the plastic. And then we would like to see some supporting ribs to allow for better stability and durability for the JEDEC tray.
And would like to acknowledge Mrs. Dallmier, Mr. Dave Dallmier, Dr. Zane Mitchell, Mr. Justin Amos, Dr. Paul Cuban, and Dr. Arthur Lebowski.
Any questions?
All right, questions?
What was your cost basis for that $1,000 for a feeder?
I found that on the internet for a new parts feeder from the actual Vanport website.
Other questions?
What was the most challenging part of the project?
That's a tough one. For the JEDEC tray, the most challenging part would have to be getting the clearances exactly perfect so that the machine wouldn't jar the chip enough to where it wouldn't know where the next chip was at, and to keep all of the dimensions between the chips in a fashion that we could still fit a number of the other 3 chips on the board. That's for the JEDEC tray, that'd be the hardest part, I'd say.
Thank you.
Any other questions?
Just have one more. And going from your SolidWorks solid model to is there any additional processing, or does SolidWorks provide a file that feeds directly into the 3D printer?
Well, you actually have to convert the drawing itself in SolidWorks to what's called an STL file. And it converts everything into triangular patterns for the 3D printer to print. And then from the computer on the 3D printer, you can actually upload the file directly from your SolidWorks file, and it prints it. It sends the file to the 3D printer itself, and you program it, and then it can print just like that.
Did you measure the top of the chips as they set in the JEDEC tray versus the top of the JEDEC tray once you had the tray built?
For the most part, most of the chips that are in there, the very top of the chip sits flush with the top surface of the JEDEC tray. We had to make it 0.4 inches thick instead of 0.25 inches thick because we shelled it 1/8 of an inch around the inside. But do you mean, do the chips stick up?
Yeah, do the chips stick up, or are they down, or are they flush?
They're flush. They're completely flush.
And you were able to measure that? Excellent. Any other questions? All right, let's give them a hand.